Okay, so in this third and final recording, we are going to look at the Virtuoso tool and the different types of analysis. So we will look at only the inverter for the transient analysis and the inverter again for the DC analysis, and we will look at one separate circuit, NMOS circuit for the VI characteristics. We will not look individually at the FO4 or inverter chain or any other gate because the procedures are the same. Okay, so the objective of this video is just for you to have a reference for the procedure. Okay, so we will continue with the next topic. So open in terminal, CSH, source. Okay, and welcome to Cadence. So all the experiments, this is the first step. So now the command is Virtuoso, Virtuoso. Okay, and press enter. And we will start off by creating the circuit the first time. So we have to start with the new library also, because in the exam or the internals you have to start from the new library itself. You might be in a new machine which has not been used before. The systems will be formatted, so you will not have the old files there. So file, new, library. Okay, give it any name you want. So for example 180 underscore nanometer, and click on attach to existing technology library and say OK. Okay, and then all these options will come. You can choose whichever one you want. So in this list, in the bottom there is GPDK 180, and for FO4 delay alone, okay, when you're doing file new library you have to do GPDK 180, but the second step is for GPDK 090 also. Okay, so we will not do that here. We will just use GPDK 180, say OK. It will not give you anything, but if you see here it will say design library 180 nanometer successfully attached to GPDK 180. So what we have done is we have created a empty library with no gates in it, but the library itself is attached to a particular technology, because the transistors have to belong to some technology, and that technology we have chosen as GPDK 180. So now we have an empty library. We have to create the circuits or the gates. In this terminology they are called as cells, because there is a standard cell library, there are cells inside the library, etc. Cell is nothing but a gate or a circuit. Okay, so for creating that we have to go for file, new, cell view. Okay, and here on this, make sure that this is your particular library that you just created. Okay, it should be that name here, and inside that you can give us cell name according to whatever functionality, and everything else is default, and say OK. This window will come. So here we can create the circuits whatever we want. Okay, and there are two types of items. One is the transistors, etc., and other is the power supply. To insert any of them we will have to do it through the command insert. And we use the I sorry, I for insert. So click on I and you will get this window, and you can choose whatever you want to insert. And first we will insert the transistors which are inside this library called as GPDK 180. Okay, and we have all these components inside that library. We want PMOS and NMOS. These are the two things, and if it is not highlighted, click on symbol. Okay, and say close, and if you move it over the palette you should see the symbol and hide. And to place it, just a single click, it will get placed. Escape. This is a NMOS transistor, and if I want a PMOS transistor, again browse PMOS, it's already in symbol, and place it here. Okay, so NMOS, PMOS, and then continue with the other components. Browse. Okay, but only thing is we will not find voltage sources here inside GPDK180 because voltage sources have no relation to the technology. They are just a voltage value or power supply. Those are available inside another library called as this analog lib, and we are going to use two types of voltage sources. One is this VDC. Okay, I'll use that first. You can put a value. I'm going to stick with 1.8 and press tab. Okay, the V I did not type, it came automatically. If you just put the number and press tab, the V will come. And hide this, and I will put this here. Okay, and again I will insert browse, and I will choose another type of voltage called as V pulse, and this is going to be my input, and I generally use the same numbers for all 0, 1.8. These are the two levels of the voltage. Period 10 nanoseconds, rise time 10 pico, fall time 10 pico, pulse width 5 nanoseconds, and this is the values you can also use for most of the experiments. Okay, and I will put this here. Okay, and last component that I need is the reference voltage or the ground, and this is all arranged in alphabetical order, so you can just search for GND, close, hide, and I will put that in the bottom. And once this is done, we can do many things. We can highlight this and move it wherever you want. Okay, you can also rotate it with this. Okay, so one thing to remember is all the minus terminals, any type of voltage source, okay, it doesn't matter, the negative terminal should be connected to ground. Don't use the negative terminal for anything else. The positive terminal is where your input signal or power supply is coming from. So now that we have that knowledge, let us connect it with the wires. And the wire is not a component that you insert, but it is just something that you can draw by clicking W on the keyboard. So see how the cursor will change when I click on W. Okay, so now wherever I want the connections, the from point, click once, remove your hand from the mouse and move it to the 2 point and click again, and you will get a wire. And you can do this if you want it to turn at a particular point, bring it there, click there and take it. Okay, and continue with all the other connections. I want it to go in a certain way, I can make it go like that also. Connect this to ground, connect this also to ground. The two transistors are connected, and finally this is also connected to ground. Okay, so almost everything is done except the fourth terminal. Fourth terminal, you can always connect it to the source terminal of each transistor. Always for NMOS transistors, the source terminal will be below. In the transistor also, you can identify it with the arrow mark. You see this arrow mark here. Arrow mark is the source terminal. Okay, so the fourth terminal is just short wire to the source terminal. Same for both transistors. Okay, even in the PMOS transistor, okay, the fourth terminal is connected to the arrow mark, which is the source terminal. So this is the complete connection. All the values have been given, the inputs, and every time we finish the circuit, okay, this button is very important, called as check and save. Check and save is very important because it will identify a lot of errors if they are there in the circuit. So every time you think you have completed the connections, click on check and save. Even if you have not completed, suppose it hangs and your circuit will be lost, right? It's like a Word document. Every time after typing 2-3 paragraphs, you might click on Control S. Do the same thing here also, okay? But at the end, it is absolutely necessary. Check and save. Like this, if no messages are coming, okay, that means the circuit is correct. Suppose I do this, click on check and save, okay? 0 errors and 2 warnings. And if you see this, the yellow will be the region where the error or warning is there. In case, obviously it's because it's hanging connection. If you want to see what the actual message is, you can click on this Virtuoso window. Okay, and this Virtuoso window will tell you what is the warning. You will see here, pin plus on instant V1 is floating net1. It's both related to the same error only. So if I do this and complete the connection, click on check and save, say schematic check completed with no errors, schematic saved. Okay, so once I have that, I can be sure that most of the things might be correct in terms of the connection. In terms of the logic, we still don't know. For that, we have to do the simulation. So how do we do the simulation? Launch the simulator called as ADEL. Okay, so ADEL mainly it has this window for the analysis. So there are different types of analysis we can do on a circuit. We are going to do transient analysis to begin with. The second part of the window is here, where we will have to tell it what are the particular signals or waveforms we want to see. So we will start with the analysis part. There is the analysis option here, analysis, choose. Okay, to begin with, we're going to do transient analysis. Stop time, I'm going to give 50 nanoseconds, and you can click on moderate, or you don't have to, that's fine, and say okay, and that will show up here. You should be able to see everything that you entered. Next is the outputs to be plotted. Select on design. Okay, so it will switch to this window, and here the outputs are just the wire voltages that we want to see for transient analysis. So in this case, the input is coming from here. Okay, so it is important to click on the wire somewhere, so like this. Okay, and the output of the inverter is here. So even though I have not marked it as an output or done anything special, it will be available at this particular node. So click on this node and go back to the ADEL window, and those two would have come. So here and here. So once all these are there, you can do the simulation. There is a green button here. Okay, press the green button. And you will get the waveforms. And once you have this, you can separate all the waveforms are together in one plot. Just split them, and you will get the two values. And if you don't remember which is input, which is output, you can go back here, press escape. Okay, and if you click on this one, it says net1. So this net1 is the input. This is the input, which means this has to be the output. So what to check in the input, sorry, not the input, the output is the value. Okay, we are designing what is called as static CMOS circuits, which means that the voltage levels at steady state of operation, meaning that the input is constant in this duration, the output should be at a perfect value of 1.8 or 0. That depends on the functionality, but it cannot be at any other intermediate values. Okay, which means that something is wrong with the connection. And next, on this plot, we can calculate the propagation delay. So how do you do that? You click on one of these plots, okay, and go for this marker, create marker, horizontal marker, and I'm going to put it at 0.9. Okay, 0.9, because that is the 50% value. And click on the second plot, do the same thing, identical, create marker, horizontal, also at 0.9. So now the propagation delay can be calculated as the difference between these two for high to low. Okay, so for example here I have 30.0136 at this point. Okay, so this transition was caused by this input going high, which went high at 30.005. so TP high to low is 30.0136 minus 30.005, that is TPHL. Similarly, TPLH, LH and HL, always it is seen for the output. Okay, don't see HL, LH here. We have to look at the output. So this is TP low to high, 35.0337 minus 35.015. And if I subtract those two, I will get TPLH. Okay, and how do I calculate TP? TP is nothing but the average of those two numbers. TP equal to TPHL plus TPLH divided by 2. So this is the procedure for calculating the propagation delay of any design. Create the circuit, check and save. Okay, after check and save, launch ADEL, give the analysis as transient, plot the outputs that you need. Once you get the waveforms, you split them into different waveforms, put the markers and calculate TPH, TPLH, and the average of those two numbers will give you the propagation delay. So next we are going to see the second type of analysis, which is the DC analysis. Okay, so VTC. Okay, so voltage transfer characteristic. Again, this is for an inverter only, and a small change in the circuit from the previous case. Remove this and insert another VDC. Okay, and check and save, and let's close this and start a fresh window for the simulation. Okay, so check and save, no problems. Launch ADEL, analysis, choose. Okay, so DC analysis, this is the DC analysis, and the way it is set up is we have to give the variable which I want to change during the analysis. In this case, we want to plot the inverter voltage transfer characteristic, and we have to give the input voltage. Okay, and we have to change that during the simulation. So select component. Okay, and we have to select this because this is the input. Okay, this is the input, this is the output. So select component, click on this and say OK, and below here there will be a window which is going to have that component and the start and stop values for that component. It's a voltage. We want the voltage to start at 0 and go till 2 volts. Okay, don't put units or anything. And this is going to be my input voltage, or in the voltage transfer characteristic, this will be the range of the x-axis, and just say OK. And we also want to plot the outputs. So outputs to be plotted, select on design. We will plot the input and the output. Okay, so we see all that here, and then press the red button. This is the voltage transfer characteristic, also in the theory the ABCDE curve, and this is the input versus the input, so it's just the x equal to y line, and where they intersect is the voltage inverter threshold voltage. That is a point where the input voltage given to the inverter comes as the output voltage. So it is a parameter of the inverter called as inverter threshold voltage. In this case it is about 750 millivolts or 700.75 volts. Okay, so if I want to change this, I want to say, the question might ask, make the inverter threshold 0.9 volts, which is VDC by 2. Okay, now it was 7.75 volts, If you want to increase the inverter threshold, you have to increase the PMOS transistor. So select the PMOS transistor. Okay. And in the keyboard, if you press Q, this window will come. The total width is 2U. Let's make it 5U. Okay. And say OK. Check and save and simulate. And if you see, it has gone up to around 855. So the theory tells us that if you want to increase inverter threshold, you make the PMOS stronger, which is what we did now. We increased from 2U to 5U. If you want to make the inverter threshold lower, you make the NMOS stronger. Okay, so this experiment relates to the inverter threshold voltage. In particular, the type of analysis is called as a DC analysis. The first analysis was transient analysis. Transient analysis is mainly used to calculate propagation delay. This is the DC analysis. Okay, the last experiment that we are going to show is related to the VI characteristic. So new cell view. Okay, and I'm going to create the circuit also. So insert NMOS. Okay, single NMOS transistor, and everything else is from analog lib, which is the source for the pulses and the ground, etc. So VDC is going to come here, and one more VDC is going to come here. Okay, and no V pulse in this experiment, and then one ground terminal. Very simple circuit in this case. Okay, and connect it with wires. Is connected to ground, the bulk terminal connected to the source terminal, input connected here, drain connected here, and finally the voltage is connected to ground. Okay, so the fourth terminal, always remember, connect it, whichever transistor it is, okay, MOS or PMOS, connect it to the terminal where the arrow mark is there. That is the source terminal for that transistor, and the bulk and source, generally if you short them, is the safest option. Okay, so this is the circuit, and what we are going to do now is basically two analysis. Okay, DC analysis to change the x-axis. Okay, and if you remember the VI characteristics, the x-axis is VDS. Okay, so in this circuit, this voltage is VDS because it is connected across the drain source, and this is VGS because it's connected across gate source. So for the VGS, okay, we cannot do double DC analysis. There's no option like that. But what we can do is we can do a DC analysis, and along with that a parametric analysis. So what is this parametric analysis? We are going to the gate voltage. I am not going to give it as any number. Okay, just going to give it as some variable VG and say okay. And what we are trying to do is we are trying to use a DC analysis, because in the DC analysis the x-axis is VDS. Okay, and sorry, not in DC analysis, in VI characteristic x-axis is VDS. So for the DC analysis I want to use this VDS, but for getting different values of VG I'm going to use this as a parameter and tell it to do a parameter analysis also. So we'll just see how to do it. It's not that complicated. So launch ADL analysis, choose. Okay, so DC analysis, component parameter. So DC component parameter, this is the x-axis, which is our VDS. So choose the right hand side voltage, say OK, give the start stop as 0, 2. Okay, and this is the first step. And in this window, the DC analysis is done. We have to plot the outputs to be plotted. Select on design. Okay, and in by design the current has to be plotted. So if I click on this, it will give me only the voltage. I cannot get VI characteristics. I'll get VV characteristics. So what I have to do is I have to click on the node. Okay, so when you click on, okay, so this we want. In this case, usually when we get this type of circle, it's a mistake, but in this case we want that. Okay, and then the last step is here. Okay, we actually have a design variable which we need to use, which is the VG that we gave. How do we get that into the simulation? Go for variables, copy from cell view, and that will come here. So we have the DC analysis. Okay, but we cannot do the analysis without giving a value for the VG. The DC analysis, every time we do it, that parameter, this will change from 0 to 2. But what is the value for VG? We have not set. So how to set that? Go for parametric analysis. Okay, and here on this, if you click, you will find our VG, and the start and stop, again you can give the same 0 to 2. Okay, and you will get the curves for the values of 0, 0 0.5, 1, 1.5, 2. Individual listing also. This is blue color, reducing much more, because 0.5 is almost lesser than the threshold voltage of the NMOS, equal to threshold voltage, so we don't get much current, and 0 obviously is coinciding with that. So this is the VI characteristics of the NMOS transistor. Starts with a DC analysis. Okay, and the DC analysis give the VDS voltage source, this one, when you're giving the DC analysis, and the rest is almost the same. Only thing, the output should be a current. And after you get these two fields in the ADL window, you get this variables copy from cell view, get the VG here. Okay, and once you get the VG here, then tools, parametric analysis, and you will get VG here. We'll get VG here. Give the from and to values, press the simulate button, and that will give you the VI characteristic of the NMOS transistor. Okay, so the rest of the experiments, the analysis are the same. Okay, it's either transient analysis, it's either DC analysis, or it's VI characteristics. The only thing that will differ is the circuit. So the steps that we showed you in today's video are the same for all the other transistor related experiments. Okay, so I'll stop this video here. Thank you.